Swayam Prabha. Digital India. Educated India.
So let's move into describing the data using the data types that we have. So three important defining characteristics that we want to use for any set of data for any given variable. First is the measure of location. It's also called the central tendency. The second is really to understand the spread of data, also called variability. And the third is the shape of data, also called distribution. As we move along, we will also understand the importance of these and as to why we are keen on these specific measures. So going back to the data that we have, the real data is this. As I said, this is only a sample of the data. So we have about 43,000 pieces. So if somebody wants to know what's the kind of price range or the kind of price that a used car would get, we have various values here. So ranging from 4,450 to 18,750, etc. There's no sense in telling somebody here are 15 different values that a particular used car can get. So we want to summarize this data into some number, which normally is the expected value. So we can take an arithmetic average of this entire piece and say that, you know, that's the kind of an average value that this used cars get. When you go to a kind of gearbox, so you might find 70% of this. So if you look at this data, probably 95% of this data is really manual gearbox, and there are only two pieces which are automatic gearbox. So the idea of a central tendency is to understand defining characteristics in terms of a value of a particular variable. So what gets used are the 3 M's, which is mean, median and mode, and a lot of times mode per se is just a variable value. So to make better sense of mode, it normally is accompanied with the proportion. So the 3 M's and proportion are the measures for location. So let's look at it through an example of even further reduced data. Supposing we had 11 different used cars, and the prices that gets quoted for these different cars are, let's say, 20,000 up to 315,000. So the mean price is really 53,909. So you say that the average price that a used car gets is $53,000. But if you look at this 53,900, there seems to be some issue with that, because it does not seem to represent most of the data pieces. So it's not close to your 15,000, 8,000, 11,000. It's nowhere near your 20,000, and it's also very far away from your 315,000 and 120,000. So the mean is computed as an arithmetic average. So you sum up all these numbers and divide by the number of items that you have. In this case, it's 11. The mean is not necessarily a value that exists within your variable set. So it can be a value which is different from what you have in the thing. But it is supposed to represent the data. So the 53,900 is the arithmetic average. So that's what actually represents the data. But we have an issue with it. So we'll deal with that issue as we move along. The median price is really the 20,000, and median is defined as a central value. So there are 11 pieces of data here. So you put this in an ascending or a descending order. So the 6th value turns out to be 20,000, and therefore the median is 20,000. You notice that the median is a lot more representative of the kind of prices cars get. So there's a lot of area where there's a 20,000, 15,000, 12. So it's much closer to the values that you are encountering in your data set. Of course, it's very far away from your 315,000 and 120,000, but that's only two pieces of data which the median does not represent well. It represents the rest of the data fairly well. The mode is the most frequently occurring value within the data set. So you find that there are two cars which are sold at $12,000 and there are two cars which are sold at $20,000. So the first thing that we learn is a mode is not necessarily a single number, so it can be multimodal. So they can be, so if you have a data set of 43,500 cars, which is what we have, there are many modes. There are many modal values that exist. Yeah. As I said, you could have a scenario where out of the 11 cars, 10 cars could be sold at 12,000, in which case the mode will still be 12,000. Whereas if there are only two cars which are sold at 12,000, and that's the highest number of recurring value, it still would be the mode. Therefore, to give a meaning to the mode, a better meaning to the mode, normally the percentage is also added. So the modal price is 12,000 and each of the modal value occurs 18.2% of the time within the data set. Yeah. So let's tackle the issue of the mean price of being 53,909, and because it's an arithmetic average, we know that this number is inflated because of these two numbers here, the 315,000 and 120,000. So they contribute substantially to the inflation of the mean to a value of 53,909, and that inflation makes it not representative of the rest of the data pieces. Yeah. So this clearly is a case of what is called extreme values, or statistically there's a term which gets used, which is an outlier. Outliers are values which are very different from the rest of the value set, values that you are encountering in a particular variable. But a word of caution here, there is absolutely no judgment that can be made about whether the value is right or wrong, because there are used vintage cars, the old, very old cars, which are probably get sold at prices even higher than $315,000. Yeah. So just because a value is anomalous and extreme within your data set, it does not mean it's a wrong data. So it's incorrect to remove the data completely. You can do it if you know that it's an error. So it is possible that there is an entry error and therefore there's an anomalous value, but you need to establish whether it's a real value or it just happens to be an extreme value which is correct. So, but it still does not solve a problem about an inflated mean. So one way to look at is really to remove the outliers for the purpose of computation of the mean. And when we do that, so when we remove the car number 9 and car number 10 from the data set and recompute the mean, we find that it's 17,555, which is very representative of all the kind of pieces of data that we have. The range between 8,000 and 25,000, majority often the 15-20, between the 12 and 20,000 range. So it's a good indicator of the kind of price a used car gets. The median gets adjusted to 15,000, which again is well representative of the data, and mode is still remains the same, 12,000 and 20,000, but occurring at 22.2% times each. So the real the learning is really the mean is an indicator of a location, is very susceptible to extreme values, and median is not. Median is also susceptible but not greatly in large data sets. Yeah. And therefore mean is not a good indicator of location in skewed distributions. Let's look at another data type, which is categorical data. So we have the same 11 cars, and we are the data is pertaining to whether there is a damage to the car or there is no damage to the car, and we find 2 of the cars out of the 11 have some damage and 9 do not have any damage. And the way to represent this data is we cannot take an average, though it's possible to put a numeric value. So you can put a value of 0 to no and 1 to yes and compute a numeric value, but that numeric value has no meaning, physical meaning. So a better way to understand this data is really to get the mode value. So the modal value of any damage is no, and there is 77%. So it's the most frequently occurring value. So we are finding that out of 9 out of the 11 cases have got no damage, and therefore so the modal value is no with 77%. Let's move on to the second area of descriptive statistics. So the choice of a measure of location, it depends on the data type, and kind of a rough guideline is if the data characteristics is nominal, you can use mode. That normally is the best measure of the middle. If it's ranked data, ordinal data, so you can have median as the best measure of data. Interval and ratio data, if there is no visible skew, and when I say a skew, in the case that we discussed, which is the price, we had two values which are extreme, very high, and if there is no such skew that exists within the data, mean or the average is the best measure of the middle. And if you have interval or ratio scale data which has got a skew, like as we had in the data that we looked at, median is the best measure of the middle. As I said, this is a rough guideline. So you need to look at the kind of distribution of the data, which we will look at in the shape of data, before you can actually decide on what is the best measure of the middle. When you have ratio data or interval data, you have the choice of using mean, median, mode. So there are multiple measures that you can use to indicate the location. The choice of measure for location not only depends on the data type, it also depends on the context and the question that gets asked to the data. To illustrate this, let's look at a very simple data set of an average rainfall in a city X over the last 10 years in centimeters. So essentially we had 10 years of data, monthly rainfall. So we averaged out this data over a period of 10 months. So the January of every year is averaged out, and the February averaged out, and so on. So the data that we have is in the month of January, on an average you get 1 centimeter of rain. In the month of May you get 3 centimeters. In the month of August you get 20 centimeters, etc. So if the question that gets asked on this data, and if the person who is looking at this data is a kind of a groundwater expert who's got the task of ensuring that all households get potable drinking water in their taps, a good measure of location would be actually the mean, because the person is interested in knowing what the total rainfall is. It does not matter when the rainfall occurs, but the total rainfall that gets fed into the soil is probably determines the kind of groundwater buildup, and therefore if he gets an average and he can multiply it by 12 to understand what is the yearly average that one gets. So that is a very appropriate measure for that person, because the question that gets asked is that are we getting good enough rains for good groundwater supplementation. But if the same data is being looked at by a tourist who wants to visit city X for the purpose of touring, what do you think would be a good measure of location? So I presume the tourist would be interested in not having her holiday rained out, so she would be looking at months where there is not too much of rainfall, or she might be interested in knowing through the year, is there a large enough period where there are very limited rains. So the measure that possibly is very useful to her could be the median, which essentially indicates that at least 6 months of the year that the rainfall is likely to be less than 4 centimeters per month. So there are periods of a calendar year where the rainfall is much lower than 4 centimeters. Now you might be wondering where the 4 centimeter comes from, because it doesn't appear in the data, because there are 12 pieces of data. There are 2 middles here, so that's number 6 and 7. So that's an average between 3 centimeters and 5 centimeters. So you get an average of 4 centimeters as median in this case. So as I said, the choice of an appropriate measure of location is not just dependent on the data type, because the data type will tell you whether you can actually do an average or cannot do an average, but it also depends on the context and the specific question that you need to answer. Now a whole series of the knowledge of domain and appropriateness of understanding what action is going to be taken on the basis of the question is very important for you to decide on what is the appropriate measure of location. What we have just seen is how to understand the location of data through the central tendency measures of mean, mode and median. So we know that the average price that gets quoted here is something which we can compute through the arithmetic average, but what we do not know is how varied the numbers are. Now we know that arithmetic average is something which you can arrive at the same number using very many different values. So we need to get an understanding about the spread of data as to how widely different the different data pieces are, and to do that we will use the following measures: range, variance and standard deviation. So these are specific measures to understand the spread of the data. So what are the kind of extreme values that we have, and within what range of the mean are these values are. So taking the same example of those 11 pieces of data with two extreme values of 120,000 and 315,000, and without them. So we had computed the arithmetic mean to be 53,909 when we had all the 11 pieces of data. We can also compute the variance, we can compute standard deviation, and we can compute the range. Before we quickly look into the differences, the different measures, the range is something which is nothing but the maximum value minus the minimum value. So that's 315,000 and 8,000 here, and it's 27,000, which is 35,000 and 8,000 here in this case. So the range tells you the difference between the max and min, and that's an indicator of how widespread the data is. Variance is a little more complex measure. It really is a kind of it's a measure which tells you how each data point is away from, how much is each data point away from the central measure, squared and summated. So we will look at the formula in the next slide, but the simple idea is, if the average turns out to be 53,909, so it's 53,909 minus 8,000. So that's the distance this data point is away from the mean. Square it, keep it, and do this for every single point and add up the whole thing and divide it by n minus 1. So that gives you the variance. The issue with variance is that it's a very large number, which makes no sense. I mean, I'm sure, to me, I can't even describe what this number is. It's that large. So when you say that the average price used car gets is 53,909, you can form an image in your mind about what kind of price. But when I indicate what the variance is, it's almost impossible for you to understand what it means. The problem with the variance is because it's got an unit which is the square of the base unit at which the data is measured. So if this is dollars, so the variance that's indicated over here is so many dollar square. Now we can't understand the physical import of a dollar square. So easier measure is the standard deviation, which is nothing but the square root of the positive square root of the variance. So which is 87,907. Again, it's not a very easy term to understand, but if you do have a large enough data and if you go through a lot of examples, you can start making better sense of the standard deviation. It tells you on an average how much a data point is away from the center. So that's what it's supposed to tell you. The whole thing makes a little better sense when we remove the 120,000 and 315,000. So, the lesson here is not only does these extreme values affect mean, it also affects the variance, it also affects the standard deviation. When we look at the formula in the next slide, we will know why it is so, because the computation of variance and standard deviation uses the mean and the distance away from the mean. So, the minute the mean is skewed, automatically the variance and standard deviation also gets skewed. So, when we do the entire exercise without the two extreme points, that makes far better sense. So, you have a mean of 17,556, the variance is still unintelligible, the standard deviation makes better sense. So, it is about 7,988, that is on an average, that is the kind of a difference you will find between different cars, and the range is 27,000. So, that is a range within which the entire values spectrum falls. So, if you have n observations x1 to xn, the sample variance is defined as value of a data minus the mean value. So, how much is each data value away from the mean, square it and summate it for all the data values divided by n minus 1, and standard deviation is nothing but the positive square root of the sample variance. The other measure that gets used for dispersion is what is called the interquartile range, and this is done through a tool called the box plot. So, essentially this tries to understand the data in terms of, so if you break up the data into 4 different quartiles, so again order the data in ascending order or descending order, and the middle 50% of the data, so you break it up into 4 quartiles. So, you have the minimum data value, you have the maximum data value, you have the 25th percent data value, the 50th percent data value, the 75th percent data value. So, the middle 50%, that is between the 25% and 75% data value, are inside the box. So, that is where those data values are lying, and you have the whiskers which are the distance between the 25th percentile data to the lowest observation and the 75th percentile data to the highest observation. So, essentially the shape of this could have been, in some case you might have a shape which is like this, which essentially says that the middle 50% occupies a lot of values. So, it is a kind of a distribution which is very compressed towards the middle with a long, it is very elongated on the y axis. Or alternatively, you could also get 50%. So, there is a concentrated 50% in the middle with very long tails. So, it goes like this. So, that is the way this data distribution would look. We will actually look at some examples of how to use this and how to interpret this at a later stage in this session. So, having gone through the measure of location, which is mean, median and mode, and then measure of dispersion, which is range, standard deviation, variance and the interquartile range. The third fundamental idea of understanding the nature of your data and the characteristics of your data is to understand the shape of data, because the mean, median, mode by itself can be misleading, as there are many combinations of data that can produce the same end result. So, you can have the same mode with just 2 out of 43,500 being the most frequent, or you can have 1000 data values which are most frequent and therefore will produce the same mode. So, to understand this, let us take the example of the average rainfall in city X that we used. We knew that the average rainfall was 10.5 centimeters. Now, you could get an average of 10.5 centimeters by using with the data value of this, where there is a very heavy rainfall of 30 centimeters, 40 and 20, etc., etc. and this is the way the graph of that would look. Or you can get an average rainfall of 10.5 with just two data values, either 11 or 10, averaging out to 10.5. So the idea is to look at these two different graphs and say that, I mean, the shape of the data here is, it's just a blob. So that's all the data is. So there are only two values which describes. Whereas here this goes like this. So there is a very different shape that's given to this data compared to this data. Or you could have a data which is spread out like this. So again, kind of bimodal data. Or you could have data of this nature, which is more like this. So there are very many different shapes that is possible given the same central tendency value, and many cases given the same central tendency and the same dispersion value also, and that could take very many different shapes. Some of the common shapes of data that we encounter, here are some examples, not the most comprehensive examples, but just to give you a flavor of the kind of different things that we can have. What's given here is really, if we ask a person for the birthday, the date, we know that that can be between 1 and 31, and for a large number of people we collect this data and plot this data. This data would look almost similar. Okay, the 29, 30, 31 obviously get a little lesser value because they don't occur with the same frequency as the rest of the data dates are. But it's very likely that it will be a very uniform distribution. So irrespective of the date of birth, the percentage of people who are born on that day is likely to be very close to 3%, because on each given day there's only 3% of the people who are born. Yeah. So this is an example of a uniform distribution. Or if we in a manufacturing setup, it's a batch process. There are many different batches of products that come out, and we count the number of defects that's coming out of each batch and plot that. And here we see that this goes kind of a normal data, but with a lot more skew in this direction here, because there are a lot many more values that are appearing on this direction. So this is kind of a normal distribution with a skew. This is a classical case of a monthly income of individuals that are plotted. So you have an average which is up here like in here, and then there's a whole series of people who are earning very large amounts of money. In fact, if you noticed any statistics related to income, most people actually indicate median and use median as a measure of location for income, and that's because that there is a skew in this direction. So there's a skew here, and so the mean value is here, but the median value is likely to be somewhere here. Again, it's a normal distribution with a skew. This is a distribution which is hours spent playing video games on weekends. So it's starting from 0 and goes up to 25. So it does not have, it has only one arm of your normal distribution. There's only one part of it, the other part of it is missing. So it's a data which is more exponential data distribution. This is a reverse exponential data, which is percentage of men spending at least 1 hour per week participating in sports or exercises, and that is plotted by age. So as age goes up, the percentage of men who actually exercise for at least 1 hour drops significantly, like this. Yeah. So again, it's an exponential distribution. So it's also, so therefore it's not sufficient for us to understand just the mean and the dispersion in terms of standard deviation, etc. It's also important for us to understand the shape in terms of how the distribution looks. Now, why is this important? Is a lot of analysis methods and the models that are used in data science and the mathematics that goes behind these computations they make assumptions about the distribution of data. So let's take regression as a method of analysis. Regression makes an assumption that the errors are distributed normally, or the population distribution of the variable is normal. So unless that assumption is valid, the usage of the tool is questionable. So if the assumption is not valid, the tool is unlikely to give you good results, and the reason is not because the tool is performing bad mathematics, but because the assumptions about the distribution of the data is wrong. Therefore, it's always important to understand the assumptions that each statistical model and tool uses, and to see whether the data that we have conforms to the shape of the data that is required for those models and tools. Most of the models have inbuilt mechanisms to understand these shapes of data, but these work as very good preliminary understanding as to whether we can whether a particular variable follows a particular distribution and has a particular shape of data, therefore whether we can use a particular tool. The two commonly used tools for shape of data, one of them is histograms, which is really used mainly for continuous variables. What is plotted here is heights of black cherry trees. So essentially you break down your entire range of data. So this varies between 60 feet and 90 feet. So you can break them up into equal intervals, or you can also break them up into unequal intervals if you wish to, because that might visually produce better pictures. But if you make them into equal intervals, you will find the width of these bars are all similar to each other, and the length is determined by the number of times the data value occurs. So it essentially is between 75 to 80 feet. We have 10 data points. So the 10 of those trees had heights between 75 and 80 feet, and only 3 had heights between 60 and 65. So this straight away gives you a kind of a graph, and many of the software that you will work with also has inbuilt capability to superimpose the kind of graph that best describes the shape of this data. You can also use unequal distributions. So if you use unequal distributions, let's say you use unequal distribution of 65 to 70 as you are this one. So what would happen is the width of this would turn into twice as much as the width of this, and the length of this would have gone up to 6. So this is the way the graph would look if you had used unequal distribution. So if you had used for the first interval you wanted 60 to 70, so now that is represented by twice the width, but the length being, the height being described by the frequency of occurrence. The second way to understand is the shape of the data. One of the very specific distribution that of particular interest is the normal distribution. So there is the PP plot and the QQ plot checks out whether your data is normally distributed, and when I say it's normally distributed, so that's a bell-shaped curve. Now you could have it like this, or you could have it like this. All of these are bell-shaped curves. So the idea is to understand whether your data follows any of these particular patterns, and to understand that you plot either a PP plot or a QQ plot, and what it tells you is this is the way your y-axis describes, that's the way your data is actually lying, and if it's a normal distribution, this is the way it ought to be lying. So essentially, if your data falls completely on the 45-degree line, that means that your data is following a normal distribution, and any aberrations are areas which are indicative of a skew or a kurtosis, which essentially is that you are having a kind of a bulk, either a skew like this, or you have a very bulky end points. So those are indicative of the kind of small movements. But if you had data which is going all over the place like this, that clearly means that it is really not a normal distribution. So the two tools, as we said, are one is histograms and the other one is the PP plot and the QQ plot. Both of them gives you an understanding. The histogram gives you an understanding about how the shape is, and the PP and QQ plot tells you whether it clearly follows a normal distribution or does not follow a normal distribution.